Have you ever noticed how a flash of lightning illuminates the night landscape for just a fraction of a second, yet somehow freezes that entire scene in your memory? That fleeting moment, gone in milliseconds, somehow etches itself into your neural circuitry with startling precision. You remember exactly where you were standing, who was beside you, perhaps even what you were thinking in that instant the sky cracked open. The question is, why? Why do our brains capture some memories with lightning-like clarity while others fade like distant thunder? The answer might surprise you, because lightning and memory formation share more similarities than scientists ever expected. Both involve electrical discharges, branching networks, and unpredictable pathways that somehow create order from chaos. Both permanently alter the landscape they touch, and both might operate according to the same fundamental physical principles that govern our universe. In 2018, neuroscientist Dr. Hannah Erickson at MIT made a discovery that sent shockwaves through both the neuroscience and physics communities. While studying the electrical patterns of memory formation in the hippocampus, she noticed something peculiar. The branching pattern of neural firing during memory consolidation looked mathematically similar to the branching patterns of lightning strikes. Not just vaguely similar, but following the same mathematical principles of something called Lichtenberg figures, those fern-like fractal patterns that electricity makes when it discharges across a surface. I remember staring at the data visualization and getting chills, Erickson recalled in her journal. It was like looking at a lightning storm happening inside a brain. The same patterns were there, the same mathematics. That can't be coincidence. What does it mean that our memories form through processes that mirror one of nature's most powerful electrical phenomena? And more importantly, what can lightning teach us about how we remember, why we forget, and whether we might someday enhance our memories by harnessing the same principles that govern thunderstorms? To understand the connection between lightning and memory, we first need to understand how each works, beginning with lightning, which is easier to observe if not to comprehend. Lightning has fascinated humans since our earliest days. Ancient civilizations saw it as divine. Thor's hammer, Zeus's bolts, the anger of the gods made manifest. But even our modern scientific understanding of lightning remained surprisingly incomplete until recently. In fact, it was only in 2003 that researchers at the New Mexico Institute of Mining and Technology finally confirmed how lightning begins, solving a mystery that had persisted for centuries. Lightning starts with a process called charge separation. Inside thunderclouds, millions of ice particles and water droplets collide. Lighter ice crystals, carrying positive charges, rise to the top of the cloud. Heavier, negatively charged particles sink to the bottom. This separation creates an enormous electrical potential, essentially a giant battery floating in the sky. When the electrical difference between the cloud base and the ground or another cloud becomes too great, around 3 million volts per meter, something extraordinary happens. The air, normally an insulator, begins to break down along paths of least resistance. This creates what scientists call a stepped leader, an invisible channel of ionized air that moves downward in discrete jumps of about 50 meters at a time, branching and searching for a path to ground. This is where it gets interesting. The leader doesn't know where it's going. It tests multiple possible paths simultaneously, branching outward in what mathematicians recognize as a fractal pattern. As physicist Dr. Martin Newman from the University of Florida puts it, lightning is essentially solving a complex three-dimensional problem in real time, finding the most efficient path through a constantly changing medium. When this branching leader nears the ground, tall objects like trees or buildings respond by sending up their own channels called upward streamers. When the downward leader connects with an upward streamer, that's when the magic happens. A complete circuit forms, and the main lightning stroke, or return stroke, surges upward at about 1/3 the speed of light, creating the brilliant flash we see. This entire process, from the first step of the leader to the return stroke, takes just milliseconds. Yet in that brief moment, temperatures in the lightning channel reach 30,000 degrees Celsius, 5 times hotter than the sun's surface. and the rapid heating causes the air to expand explosively, creating thunder. What's remarkable is that each lightning bolt is unique, following a path determined by countless variables, from air density to moisture content to the electrical properties of the surrounding atmosphere. No two lightning bolts ever follow exactly the same path, yet all obey the same physical laws. Now, compare this to what happens when you form a memory. When you experience something, let's say witnessing a lightning strike, your brain doesn't simply record it like a video camera. Instead, different aspects of the experience are processed by different brain regions simultaneously. The visual cortex processes what you see, the auditory cortex handles the thunder, the amygdala registers your emotional response, and so on. These different brain regions communicate through electrical signals that travel along neural pathways. When neurons fire together, they strengthen their connections in a process neuroscientists call long-term potentiation, or LTP. This is the physical basis of memory. Neurons that fire together wire together. But here's where Dr. Erickson's insight becomes crucial. The pattern of neural activation during memory formation isn't random. It follows specific pathways of least resistance through your brain, branching and connecting in patterns that look strikingly similar to how lightning branches through the sky. Memory formation is essentially an electrical phenomenon, explains Dr. Erickson. Neurons communicate through electrochemical signals. When you're forming a memory, what you're really doing is creating a specific pattern of electrical activity that can be reactivated later. This is where we need to meet Catherine Turner, a 42-year-old high school science teacher from Portland who experienced something extraordinary during a thunderstorm in 2016. Turner was grading papers on her porch when lightning struck a tree in her yard, just 30 meters away. The experience was terrifying, but what happened afterward was even more unsettling. For weeks after the lightning strike, I had these incredibly vivid flashbacks, Turner explains, not just of the lightning itself, but of random memories from my childhood. Things I hadn't thought about in decades. My grandmother's kitchen, a birthday party when I was 7, the smell of my first classroom. They weren't just vague recollections. They were hyper-realistic, like I was actually there again. Turner's case intrigued neurologist Dr. Howard Evans at Oregon Health Sciences University, who had been studying similar phenomena in other patients exposed to strong electromagnetic fields. What Catherine experienced suggests something fascinating about memory storage and retrieval. Evans notes, "It's as if the electromagnetic pulse from the lightning temporarily altered the normal barriers to memory access in her brain, allowing dormant memories to resurface." Turner's experience raises a profound question. If memories can be spontaneously reactivated by electrical phenomena outside the brain, what does that tell us about how they're stored in the first place? And more importantly, could understanding lightning help us better understand, and perhaps even enhance, human memory? To truly appreciate the connection between lightning and memory, we need to zoom in on the patterns they both create. This is where things get visually striking and mathematically profound. When lightning strikes a surface like sand or certain types of photographic film, it creates what are called Lichtenberg figures, intricate branching patterns that look remarkably like the branching of trees, river systems, or the veins in a leaf. These aren't random designs. They follow specific mathematical properties of fractal geometry, self-similar patterns that repeat at different scales. Benoit Mandelbrot, the mathematician who pioneered fractal geometry in the 1970s, was fascinated by these patterns. He recognized that Lichtenberg figures follow what's called a power law distribution, a mathematical relationship where the probability of finding a branch of a certain size is inversely proportional to its size raised to some power. In simpler terms, there are many small branches, fewer medium-sized branches, and very few large branches, but all following a precise mathematical ratio. The most intriguing aspect is that these patterns emerge spontaneously whenever electricity seeks the path of least resistance through a medium. The electricity doesn't plan these beautiful patterns. They emerge naturally from the physics of electrical discharge combined with the properties of the medium it's traveling through. Now, here's where Dr. Erickson's discovery becomes truly revolutionary. When she used advanced imaging techniques to map the electrical activity in the hippocampus, a seahorse-shaped brain structure crucial for memory formation, during memory consolidation, she saw patterns that followed the same mathematical principles as Lichtenberg figures. The similarity wasn't just superficial, Erickson emphasizes. We ran the numbers and found that neural activation during memory formation follows the same power law distribution as lightning strikes. The branching patterns of neural firing statistically match the branching patterns of lightning. This finding suggests something profound. Both lightning and memory might be governed by the same underlying physical principles, specifically what physicists call path-dependent criticality. This is a fancy way of saying that both systems exist at a critical balance point between order and chaos, and the specific path taken depends on both the current state of the system and its history. To test this theory, Erickson collaborated with physicist Dr. Leon Masters at the Santa Fe Institute, an organization dedicated to studying complex systems. Together, they developed computational models that could simulate both lightning strikes and memory formation using the same mathematical framework. What's fascinating is that when we apply the same equations to both phenomena, we get realistic results for both, Masters explains. The same mathematical model that accurately predicts how lightning will branch also predicts patterns of neural activation during memory formation. That's not something you'd expect if the similarities were merely coincidental. This connection became even more compelling when researchers at Tokyo University made an unexpected discovery in 2019. They were studying patients with certain forms of epilepsy, a condition characterized by abnormal electrical activity in the brain. Using high-resolution EEG recordings, they noticed that just before a seizure, the electrical patterns in the brain began to resemble the early stages of lightning formation, complete with what looked like neural equivalents of stepped leaders branching out across brain regions. Dr. Yuki Tanaka, who led the study, explained, "It was as if the brain was experiencing an electrical storm. The patterns of spreading electrical activity followed the same branching logic as lightning, but instead of seeking ground, they were seeking paths of neural connectivity." This research revealed something critical about both lightning and memory. Both phenomena involve what physicists call percolation, the process by which something filters through a complex medium by following connected pathways. In clouds, it's electricity moving through varying densities of air, water, and ice. In brains, it's electrical signals moving through networks of neurons with varying connectivity strengths. But there's an important distinction that makes memory even more remarkable than lightning. While lightning's path is determined by the physical properties of the atmosphere at that moment, memory pathways are shaped by past experience. Every time you remember something, you slightly alter the physical structure of your brain, creating new pathways for future electrical signals to follow. This is why memories evolve over time, explains Dr. Erickson. Unlike lightning, which leaves only temporary ionization in the air, neural electricity leaves a physical trace, strengthened connections between neurons. The next time a similar pattern of activation occurs, it's more likely to follow the same path, reinforcing the memory further. To visualize this, imagine walking through fresh snow in a field. The first time you create a new path. The second time, it's easier to follow your existing footprints. With repeated journeys, that path becomes increasingly well-defined. Memory works similarly, but with electrical signals carving paths through neural networks rather than feet through snow. This explains something that has long puzzled memory researchers. Why memories that are frequently recalled become more resistant to forgetting, but also subtly change over time. Each recall isn't just retrieving a static record. It's recreating a pattern of electrical activity that further shapes the neural landscape. For Catherine Turner, the science teacher who experienced vivid memory flashbacks after witnessing a nearby lightning strike, this research offered a possible explanation for her experience. Dr. Evans suggested that the electromagnetic pulse from the lightning might have temporarily altered the electrical properties of my brain, she recalls. It's like the lightning outside somehow resonated with the electrical patterns of my stored memories, making them easier to access. While Turner's case remains anecdotal, it aligns with research showing that transcranial magnetic stimulation, TMS, a technique that uses magnetic fields to influence electrical activity in the brain, can temporarily enhance memory recall in laboratory settings. The connection between external electrical phenomena and memory access is real, even if not fully understood. But perhaps the most profound implication of the lightning memory connection came from an unexpected experiment involving actual lightning and artificial neural networks. In 2020, a multidisciplinary team from MIT, Caltech, and the University of Florida embarked on an unprecedented experiment. Led by Dr. Erickson and atmospheric physicist Dr. James Rodriguez, the team set out to test whether the patterns of real lightning strikes could be used to train artificial neural networks. The experiment, dubbed Living Lightning, used high-speed cameras and electrical sensors to capture the exact branching patterns of lightning strikes at the University of Florida's Lightning Research Center. This facility features tall towers that intentionally attract lightning for research purposes, allowing precise measurements of natural strikes. "We were essentially using lightning as a teacher," explains Rodriguez. "We wanted to see if the natural intelligence embedded in lightning's pathfinding could enhance machine learning algorithms." The team recorded data from over 200 lightning strikes and used these branching patterns as training inputs for an artificial neural network designed to solve complex optimization problems. Specifically, finding efficient paths through complicated three-dimensional spaces. They then compared the performance of this lightning-trained AI to conventional algorithms. The results were stunning. The lightning-trained networks consistently found solutions that were 15 to 22% more efficient than traditional algorithms when tested on a variety of problems, from routing logistics to protein folding prediction. Lightning has been solving complex path optimization problems for billions of years, notes Erickson. It's had a lot of practice finding the most efficient route through a complex, changing medium. Our experiment showed that there's a kind of embedded intelligence in these natural electrical phenomena that we can learn from. But the team took the experiment one step further. They reversed the process using their lightning-trained AI to predict how memories might form in the human brain. They fed the AI information about existing neural connections in sections of the hippocampus, then asked it to predict which pathways would be most likely to strengthen during the formation of new memories. When they compared these predictions to actual brain imaging data from volunteers learning new information, the correlation was remarkable, far better than previous models of memory formation had achieved. It was like the AI had learned something fundamental about how electricity navigates complex systems, says Erickson. And since both lightning and memory involve electricity finding paths through complex media, the principles transferred from one domain to the other. This groundbreaking work caught the attention of Howard Evans, the neurologist who had been studying Catherine Turner's unusual memory experiences following her lightning exposure. Evans wondered, if lightning patterns could improve artificial memory systems, could they also help understand or even treat human memory disorders? Evans approached the Living Lightning team with a radical proposal. What if they applied their findings to develop new therapeutic approaches for memory disorders like Alzheimer's disease or certain forms of amnesia? Memory disorders often involve disruptions to the normal electrical pathways in the brain, Evans explains. What if we could use our understanding of how lightning finds new paths to help design interventions that could restore or create alternative memory pathways? This led to a collaboration that would bring Catherine Turner back into the research in an unexpected way. Since her experience with the lightning strike, Turner had become fascinated with the science behind what had happened to her. When Evans told her about the Living Lightning project, she volunteered to participate in a pilot study testing a new form of targeted transcranial magnetic stimulation guided by the lightning-trained AI. The idea was to use magnetic pulses to temporarily alter the electrical properties of specific brain regions, Evans explains. But instead of the standard TMS protocols, we used patterns derived from the lightning research, specifically patterns that our AI predicted would be most effective for enhancing memory retrieval. Turner underwent a series of sessions where these lightning-inspired magnetic stimulation patterns were applied while she attempted to recall specific memories from different periods of her life. The researchers carefully monitored her brain activity during these sessions using functional magnetic resonance imaging, fMRI. The first session was subtle, Turner recalls. I was trying to remember details about a family vacation from when I was 12, and suddenly it was like a door opened in my mind. I could remember conversations, the smell of the hotel room, even what book I was reading by the pool. Details I hadn't thought about in 30 years. As the sessions continued, the effect became more pronounced. Turner found herself able to recall not just isolated memories, but entire sequences of events with remarkable clarity. More significantly, fMRI scans showed that her patterns of brain activation during these enhanced recall sessions closely resembled the branching patterns predicted by the lightning-trained AI. What we were seeing was essentially controlled versions of what Catherine experienced after the actual lightning strike. Evans notes, by applying electromagnetic stimulation in patterns that mimicked natural lightning's branching behavior, we were helping her brain find pathways to memories that had become difficult to access. The implications of this research extend far beyond individual cases like Turner's. If memory truly operates according to principles similar to those governing lightning, it suggests new approaches for understanding and potentially treating a range of neurological conditions. For instance, in Alzheimer's disease, one of the earliest symptoms is difficulty forming new memories. The living lightning research suggests this might be understood as a problem of electrical pathfinding in the brain, neural electricity struggling to forge new paths through a medium that has become less conductive due to protein buildups and cell death. If we think of memory formation as an electrical pathfinding problem similar to lightning, Erickson explains, then we might develop interventions that help neural electricity find alternative routes around damaged areas, just like lightning will find an alternative path to ground if its initial path is blocked. This reframing of memory disorders as electrical pathfinding problems represents a significant shift in perspective for neuroscience. Rather than focusing exclusively on the chemical and cellular aspects of these conditions, it suggests paying equal attention to the electrical dynamics of how information flows through neural networks. But the lightning memory connection goes even deeper than practical applications. It points to something fundamental about how nature processes information, something that may tie together phenomena as diverse as lightning strikes, neural networks, river formation, and even the growth of plants. What do lightning bolts, neurons, river deltas, tree branches, blood vessels, and lung airways all have in common? They all form branching networks that efficiently transport something, electricity, information, water, nutrients, or oxygen, through a three-dimensional space. And remarkably, they all tend to follow the same mathematical principles when they branch. This observation leads to a profound insight. Branching may be nature's universal solution to the problem of efficient distribution through a complex medium. It's a pattern that emerges spontaneously whenever something needs to find the most efficient path through a complicated space. Nature keeps reinventing the same solution across completely different domains, explains theoretical physicist Dr. Rachel Wong of Caltech, who joined the Living Lightning Project in its second phase. Whether it's electricity moving through air, water flowing through a landscape, or neural signals traveling through the brain, the mathematics of efficient branching remains consistent. This consistency likely reflects underlying physical constraints that transcend the specific materials involved. When anything, electricity, water, or information, needs to move efficiently through a complex, heterogeneous medium, branching networks naturally emerge as the optimal solution. It's like nature discovered a mathematical truth and then applied it everywhere. Wong continues. And the fascinating thing is that these branching patterns aren't designed by any central intelligence. They emerge spontaneously from local interactions following simple rules. This principle is evident in how lightning branches as it searches for a path to ground, but it also explains why our memories form along branching neural pathways. In both cases, the branching pattern reflects an efficient solution to a complex distribution problem. For memory, this efficiency is crucial. Your brain must store vast amounts of information in a way that allows quick retrieval when needed. Branching networks of neurons provide an elegant solution. They allow information to be stored in a distributed yet organized manner, with related concepts connected through shared branches. This explains why memories are both robust and fragile. Because memories are stored across distributed networks rather than in single locations, they can survive damage to small portions of the network. Yet specific branches can be weakened or lost over time if not regularly reinforced, leading to forgetting. Understanding memory as a branching electrical phenomenon similar to lightning also helps explain some of its most mysterious aspects, like why emotional memories are particularly vivid and durable. Emotional arousal essentially amps up the electricity, explains Erickson. When you're emotionally aroused, whether through fear, excitement, or joy, your brain releases neurotransmitters that increase the electrical activity of neurons. This is like increasing the voltage in a lightning strike, allowing it to branch more extensively and create stronger pathways. This explains why people often have such vivid memories of emotional events like witnessing a lightning strike, experiencing a car accident, or even their first kiss. The heightened electrical activity during these events creates stronger, more extensive branching patterns in neural networks, patterns that remain easier to reactivate later. The lightning memory connection provides a new lens for understanding another mysterious aspect of memory: why sleep is so crucial for memory consolidation. During deep sleep, your brain engages in a process called memory consolidation, where the day's experiences are integrated into long-term memory. Neuroscientists have long observed that this process involves repeated reactivation of the neural pathways formed during waking hours. Sleep is like a controlled electrical storm in your brain, explains Evans. During specific sleep stages, waves of electrical activity sweep through the brain, reactivating and strengthening the branching pathways formed during learning. It's similar to how small preliminary discharges precede the main lightning strike, preparing the path it will follow. This perspective suggests that sleep disorders might impair memory by disrupting the normal patterns of electrical activity needed for proper consolidation, like a thunderstorm that never fully develops, leaving only weak, fragmented pathways. For Catherine Turner, understanding these principles helped explain not only her unusual memory experiences following the lightning strike, but also a pattern she had noticed in her students over years of teaching. I've always observed that my students remember material better when they're emotionally engaged, when there's a sense of wonder or excitement in the classroom, she notes. Now I understand that I'm essentially creating conditions for stronger electrical branching in their brains. I'm amping up the voltage of their neural lightning. Turner began deliberately incorporating this understanding into her teaching methods, using dramatic demonstrations, storytelling, and strategic surprise to create emotional engagement at key learning moments. She also began emphasizing the importance of sleep before exams, explaining to students how their brains electrically reinforced memories during deep sleep. Test scores have improved significantly, she reports. But more importantly, students recall the material months later, showing better long-term retention. The lightning model of memory also offers insight into another mysterious phenomenon: the sudden flash of insight that sometimes occurs when solving problems, what we often call the eureka moment or the aha experience. These moments feel like lightning strikes in the mind, sudden, illuminating, and often accompanied by a surge of emotion. Neuroscience research suggests they actually involve a rapid reconfiguration of neural activity, where previously unconnected branches of memory suddenly form a new connection. When you have that flash of insight, what's happening is very similar to when a lightning bolt finally completes its path to ground, explains Wang. You've had all these step leaders, tentative pathways of thought, branching through your neural networks, and suddenly one of them connects, completing the circuit and releasing a surge of electrical activity that lights up your consciousness. This explains why insight often comes when we're relaxed or focusing on something else entirely. Conditions that allow our brains to explore more distant, less obvious branching possibilities rather than repeatedly traversing the same well-worn neural paths. But perhaps the most profound implication of the lightning memory connection involves the nature of consciousness itself. If memory formation operates according to principles similar to lightning, what about consciousness, our moment-to-moment awareness and sense of self? This question led Dr. Erickson's team to expand their research beyond memory to examine the electrical patterns associated with conscious awareness. Using high-density EEG recordings that could capture brain activity with millisecond precision, they observed something remarkable. Consciousness appears to involve continuous branching patterns of electrical activity that bear striking similarities to an ongoing lightning storm. Consciousness isn't a place in the brain. It's a process, explains Erickson. Specifically, it seems to be a continuous process of electrical branching and integration across neural networks, like a perpetual lightning storm where branches continuously form, connect, and reconfigure. This perspective aligns with leading theories of consciousness like the global workspace theory and integrated information theory, which propose that consciousness emerges from the integration of information across multiple brain regions. The lightning model adds a crucial insight. This integration follows specific patterns of electrical branching that may be governed by the same physics as lightning. When you're conscious, your brain is constantly generating something like sheet lightning, branching patterns of electrical activity that spread across neural networks, integrating information from multiple sources. Erickson continues. When certain branches connect, forming complete circuits between previously separate networks, that's when information enters conscious awareness. This model helps explain the fluctuating nature of consciousness, why our awareness seems to flow from one focus to another rather than remaining fixed. Like lightning, conscious attention follows paths of least resistance that continuously shift based on both external stimuli and internal brain states. It also offers a new way to understand altered states of consciousness, from meditation to psychedelic experiences to dreams. Different states of consciousness might be understood as different patterns of neural lightning, suggests Evans. Meditation, for instance, might calm the storm, reducing the chaotic branching to a more organized, rhythmic pattern. Psychedelics, on the other hand, might lower the threshold for branching, allowing neural lightning to explore paths it normally wouldn't, creating new connections between previously isolated networks. For Catherine Turner, this research provided insight into another aspect of her post-lightning experience, what she described as moments of extraordinary clarity that occurred randomly in the weeks following the strike. Sometimes I'd be doing something mundane, like washing dishes, and suddenly everything would seem incredibly vivid and meaningful, she recalls. Colors were brighter, sounds more distinct, and I had this profound sense of connection to everything around me. It was like being hyper-awake. Evans suggests these experiences might reflect temporary changes in Turner's neural electrical activity following her proximity to the lightning strike, perhaps a recalibration of the normal thresholds for neural branching that temporarily enhanced the integration of sensory information into consciousness. While Turner's experiences gradually returned to normal, they left her with a lasting appreciation for the fragility and wonder of conscious experience, and a new understanding of the electrical nature of her own mind. I used to think of my thoughts as something separate from my physical brain, she reflects. Now I understand that my consciousness, my memories, my very self, they're all patterns of electricity branching through networks of cells. Not so different from lightning branching through the sky. There's something humbling about that, but also wonderful. This perspective on consciousness as a lightning-like process of electrical branching has profound implications for how we understand the relationship between brain and mind, and potentially, for how we might someday treat disorders of consciousness like coma or certain forms of dementia. If consciousness emerges from specific patterns of electrical branching across neural networks, Then interventions that help restore or recreate those patterns might help recover consciousness in damaged brains, like creating artificial lightning paths where natural ones have been disrupted. Indeed, recent research with minimally conscious patients has shown that certain forms of electrical stimulation can temporarily enhance awareness, perhaps by facilitating the branching patterns necessary for conscious integration. The lightning model offers a theoretical framework for refining and improving such interventions. But the implications extend beyond clinical applications to fundamental questions about the nature of mind. If consciousness involves lightning-like electrical branching, might similar processes create forms of integration in other complex electrical systems, from global weather patterns to the internet? This question leads to what philosophers call the hard problem of consciousness. Why electrical activity in neural networks should give rise to subjective experience at all. The lightning model doesn't solve this problem, but it reframes it in intriguing ways. Perhaps consciousness isn't something magic that happens only in brains, suggests Wang. Perhaps it's a fundamental property of certain types of complex, self-organizing electrical systems that reach a critical threshold of integration. The lightning comparison reminds us that the physics of electricity creating patterns through complex media isn't unique to brains. It's happening all around us in nature. This perspective doesn't claim that lightning is conscious, but rather that consciousness and lightning might be different manifestations of the same underlying physical principles. Principles that govern how electricity creates branching pathways through complex systems. For Dr. Howard Evans, who has spent decades working with patients with memory and consciousness disorders, this framework offers not just scientific insight but a kind of poetic understanding. When I watch a lightning storm now, I see it differently, he reflects. I see nature working out the same mathematical problems that our brains solve every time we form a memory or have a conscious thought. There's something profound about recognizing that connection, that the same principles shaping lightning bolts might also shape our minds. The recognition that memory and lightning share underlying principles opens exciting frontiers for both neuroscience and technology. Researchers are now exploring how this understanding might lead to new treatments for memory disorders, enhanced learning techniques, and even brain-inspired computing architectures. One of the most promising applications involves a technique called guided neural branching, GNB, developed by Erickson's team based on their lightning research. This approach uses precisely targeted electromagnetic stimulation to influence the branching patterns of neural activity during memory formation and retrieval. Traditional brain stimulation methods tend to be rather blunt instruments, explains Erickson. They activate or inhibit specific brain regions, but don't account for the complex branching dynamics of how information actually flows through neural networks. GNB is different. It's designed to work with the brain's natural branching tendencies, gently guiding neural electricity along more optimal pathways. Early clinical trials of GNB for mild cognitive impairment, often a precursor to Alzheimer's disease, have shown promising results. Patients receiving the lightning-inspired stimulation patterns showed a 32% improvement in memory performance compared to control groups, with benefits persisting for weeks after treatment. We're essentially helping the brain's electrical activity find paths around damaged areas, says Evans, who led the clinical trials. Like lightning finding an alternative route when its primary path is blocked, neural activity can often find new ways to encode and retrieve information if given the right guidance. The lightning memory connection has also inspired new approaches to artificial intelligence. Traditional computer architectures process information very differently from brains, using sequential operations rather than parallel branching networks. But a new generation of neuromorphic computing systems is being developed that mimics the branching, lightning-like dynamics of neural processing. We're literally building lightning into computers, explains computer scientist Dr. Mei Chun, who joined the Living Lightning team to develop practical applications of their research. These systems allow electricity to find its own pathways through specialized hardware that supports complex branching, rather than forcing it through predetermined circuits. The result is artificial neural networks that can solve certain types of problems much more efficiently than traditional computers. These lightning-inspired computers are particularly good at tasks involving pattern recognition, adaptive learning, and solving problems with multiple possible solutions, precisely the types of cognitive challenges at which human brains excel. For education, the lightning model of memory suggests new teaching strategies that work with, rather than against, the brain's natural tendencies. Catherine Turner has been at the forefront of applying these insights in the classroom. Understanding memory as a branching electrical phenomenon changes how you approach teaching, Turner explains. It's not about hammering information into students' brains. It's about creating conditions where their neural lightning can form optimal branching patterns. This approach involves carefully timed emotional engagement, strategic spacing of information to allow sleep-based consolidation, creating meaningful connections between new material and existing knowledge networks, and providing the right conditions for those aha moments of insight. Turner has developed what she calls lightning learning protocols that incorporate these principles, and has been training other teachers to implement them. Schools adopting these methods have reported significant improvements in both test performance and long-term retention. The most rewarding part is seeing students who previously struggled with memory-intensive subjects suddenly flourish, Turner notes. When you work with how their brains naturally form memories rather than against it, learning becomes more efficient and more joyful. Perhaps the most speculative but intriguing frontier inspired by the lightning memory connection involves the possibility of external memory augmentation, technology that would interface directly with the brain's electrical branching systems to enhance memory capacity or retrieve lost memories. Researchers at the University of California, Berkeley have developed prototype memory prosthetics using networks of microelectrodes that can record the specific branching patterns of neural electricity during memory formation, store these patterns, and later reintroduce similar electrical patterns to facilitate recall. In early tests with epilepsy patients who already had electrodes implanted for medical monitoring, these devices improved memory performance by up to 37% for specific types of spatial and factual memory tasks. We're essentially capturing lightning in a bottle, explains Dr. Vincent Chong, who leads the Berkeley research. We record the unique electrical signature of a memory being formed, then can reintroduce a similar pattern later to help the brain retrace those same branching pathways. While these technologies remain in early stages of development, they point toward a future where our understanding of memory as a lightning-like electrical phenomenon might lead to remarkable new capabilities. From treating amnesia to enhancing learning to preserving memories that might otherwise fade with age or disease. Yet, as with any powerful technology, these developments raise important ethical questions. If memories are electrical patterns that can be recorded, enhanced, or potentially even transferred, what does that mean for privacy, identity, and the authenticity of experience? Who should control access to such technologies, and how might they change what it means to be human? These questions have no easy answers, but the scientists involved in this research emphasize the importance of developing ethical frameworks alongside the technology itself. Understanding memory as a form of neural lightning doesn't reduce its significance or beauty, insists Erickson. If anything, it makes memory more wondrous, a phenomenon that connects us to fundamental patterns in nature. But with that understanding comes responsibility to ensure these insights are used to heal and enhance, not to manipulate or control. As our exploration of the connection between lightning and memory comes to a close, we return to Catherine Turner, whose unexpected encounter with lightning sparked a journey that would transform both her understanding of her own mind and her approach to teaching. 5 years after the lightning strike that temporarily altered her memory, Turner stands before her high school science class, teaching a unit on electricity and the brain. On her desk sits a small Lichtenberg figure, a beautiful branching pattern burned into a piece of acrylic by a high-voltage electrical discharge, resembling a frozen lightning bolt. When you remember this class tomorrow or next week or years from now, she tells her students, what's happening in your brain isn't so different from what created this pattern. Electricity finding its way through a complex landscape, creating branches that connect and illuminate. Your memories are lightning preserved in living tissue. Turner's students lean forward, engaged by both the striking visual aid and the profound concept it represents. She can see the spark of understanding in their eyes, the neural lightning of insight branching across their minds. Later that evening, Turner meets with Hannah Erickson, Howard Evans, and other members of the research team who have gathered for a conference at the university where Turner now occasionally lectures on educational applications of their work. As they share updates on their latest findings and applications, a spring thunderstorm rolls in. The group moves to the window, watching as lightning illuminates the darkening sky. Each flash reveals a different branching pattern, unique, yet following the same fundamental principles that their research has connected to the workings of memory and mind. It's humbling, Evans remarks quietly. Every thought we have, every memory we cherish, all following the same patterns as those lightning bolts. As though nature developed one elegant solution and applied it everywhere from storms to consciousness. Turner nods, remembering how her own brushes with both literal and metaphorical lightning have transformed her understanding of herself. What fascinates me most is the permanence, she says. Lightning seems so fleeting, yet it leaves traces, both in the physical landscape and in anyone who witnesses it. Just like memories. There's a beautiful symmetry to it, agrees Erickson. Lightning creates branching patterns in the sky that last for milliseconds. Yet when we witness them, our brains create similar branching patterns that can last a lifetime. As they watch the storm, each lightning flash serves as a visible reminder of the invisible electrical branching happening continuously in their own brains. The neural lightning that forms their memories, thoughts, and conscious experiences. In that moment, they share a profound appreciation for the elegant unity underlying such seemingly different phenomena. A recognition that the same principles governing electricity's path through the atmosphere also guide the formation of our most precious memories and the emergence of our conscious minds. Nature writes with electricity, whether across storm clouds or through neural networks, and in that writing we find not just information but meaning. Patterns that connect, illuminate, and endure. Perhaps this is the most profound lesson that lightning can teach us about memory. Both are manifestations of a universe where energy, flowing through complex systems, creates patterns that transform chaos into meaning. In understanding one, we gain insight into the other, and in that understanding, we glimpse the underlying unity of the natural world and our place within it. Like lightning branching across the sky, memories branch through our minds, illuminating our inner landscape and connecting past to present. Fleeting electrical phenomena that somehow capture the essence of who we are and what we have experienced, preserved in patterns of connectivity that can last a lifetime.